Okay, in this lecture we will talk a bit about linear maps or linear transformations, essentially between two vector spaces. So to begin with, let's start with a map. Say I have a space U, I have a space V, and there is a map F between a vector space U and V, and both could be defined over the same field. They need not be of the same dimensions and so on. So this map F is linear if and only if the following definitions. You have the homogeneity, you have additivity, and the superposition things, right. So this something like this. So for example, say if x is an element here, f of x is an element of over here. So if you add two elements here, x and y, they will be added like in this way, right. So in fx plus fy. So it's the same as adding. So this plus this is the same as adding this and this in the codomain space. So in general, if I have vectors u1 till un and numbers c1 till cn belonging to f, so something like this. So this is like a generalization of what we have written over here. So this is something which defines what are linear maps, and linearity we would have studied in linear circuits, and an obvious thing to check for is the principle of superposition. That exactly holds here also. So what are few basic examples? One is the identity map, where I just start from x. So I have say both my domain and codomain are V. So I start from a x and then I come back to x, like the identity map, and it's really trivial to check the properties of superposition. Second is a zero transformation, right, that f of x actually maps to 0. Multiplication by scalar is also an easier thing to check. The transformation defined by the inner product such that f of x is x times z is also a linear transformation. Similarly, now if I look at different dimensional subspaces, say a map going from R2 to R3 such that f of x, which has takes two elements and gives me a three-dimensional vector defined by such a map, is also a linear transformation, right. So in general, I can write this as say some y equal to a times x. However, what is not a linear map is if I just put some constant vector here or some constant number, right. So if I just talk in terms of real line, I have this is a linear map y equal to mx, but as soon as I add c, this is no longer a linear transformation, essentially because of this term here. Okay, so once we have defined the map f, it's important to define two other concepts. So first is called the image of f. So image of f. So again, let's draw the picture. Okay, so pictures are here. So the image of f is the set of all y's here, which come from V, such that this y is comes from some x in the space U, right, and this should hold for all x belongs to U. So that is called the image of this map f. Similarly, the kernel of a map is defined as the set of all x's which map to the 0 vector here, or the 0 element in V, right. So for all, so the set of all x, so this here just one, so there could be several of these x's which can map here, this could be some here and so on. So that is called the kernel, and it's easy to check, and it's a small proof which you can do by yourself, is that the image is a subspace of V, and it is trivial to check that it satisfies the conditions of a subspace, that all the properties of V over F are carried on to the subspaces. Similarly, the kernel is a subspace of U, right. This is the set of all x's which come from U. This is also a subspace, and it's easy to check that it also satisfies the conditions for a subspace. Well, I'll not do the proofs for this, but this you can do as an exercise for yourself. Okay. Okay. So what are the properties, or or are there any applications for this of defining the image and a kernel? So let us start with a system of m equations, right. So let us say that x belongs to some space u, b belongs to some space v, and a I k here defines the linear transformation. If I just denote it as a transformation, a of x will give me this number b, and a system of linear equations would solution would mean, does there exist x such that which under this transformation gives me the number b. Okay. So okay, what can we say about the solutions of this, right. So the solution, so in general, if I look at it as a set of linear equations written here, a x equal to b, you would say, well, invert that x equal to a inverse b is a solution, but a need not always be invertible. So what can we say about existence of solutions of this, right. So first is, for a solution to exist, this b must be in the image of a. Just for a solution to exist, there can be multiple solutions also, right. Just for the solution to exist, this one, right, that the b is in the image of f. Okay. When will it be a unique solution? The unique solution would be when the kernel of this map is the 0 vector, right, and there is no solution if b is not in the image of f. Again, I will not do proofs of this, but let us assume that there are two solutions, right. A x1 gives me b, a x2 also gives me b. Okay. A x1 minus x2 will be 0, right, sorry, the 0 vector, right. So here I can say that x1 minus x2 is in the kernel of A. Okay. Now from here you can kind of verify this statement, that the solution is unique if and only if the kernel of f or the A in this case consists of the 0 vector, right. So if x1 and x2 should be unique, then x1 minus x2 is actually 0, that they will be equal. So a little verification of this, but you can write down the details for yourself and check. Okay. So let us look at the linear space of all transformations. So let us, I just take u and v, like the usual subspaces, and I club together a set of all linear transformations of u into v, again defined over a field f. So say for example, if f and g are two linear transformations, say I have a f here, I have a g here, then we can define things like this, that f plus g, so this is f, this is g. So f plus g from x will be the same as adding f of x and g of x, similar to the function spaces things that we saw earlier. Similarly, I can do it with the scaling, right. So c times f acting on x will be f of x first and then multiply it by c. So it can be verified that f plus g and this c times f are also linear transformations on f. Very simple to verify the properties that we had seen over here, right. So I will not go into the details of that, but I think it should be kind of obvious now. And therefore, the space L u v, which is the set of all linear transformation of v into u, of u into v, is by itself a linear space with the 0 transformation as a 0 element. That is a kind of a concluding trivial statement to show that L u v is actually a linear space of transformations. Okay. So in the linear case, so what are the representations of this is A here or in general the F's here? So we will look at one very special class, or which will also be the general form of it, is to look at matrices and its elements as linear maps. So say something like this, right. So this map essentially from Ax equal to b was essentially a map where all these A's were defined as elements of a matrix A. Okay. So let us consider now a linear map from f going from v, so u to v, and let us assume that they are of dimension n and m, not necessarily of equal dimensions. Each space is equipped with a basis. The basis need not be unique, but just assume that there is a set of bases u1 till un which belongs to u, and v1 till vm which belongs to v. Okay. So, any element x belonging to u can be written as x is summation I equal to n xi ui, right, just from the definition of the basis. Now, if I take this map, right, so let us say f of x is f of ui. Now, what I know that I am looking here as linear maps, right. So, this will be summation I equal to 1 to n, and because of the linearity this will be f of ui. Okay. Now, this f of ui, what does f do? It takes elements from u and gives me elements in v. So, f of ui will necessarily belong to v, right. So, what does this mean? That each of these basis elements u1, u2 until un transforms to some vector v under this linear transformation f, right, and therefore, this f of ui should have a unique representation in terms of this basis v1 till vm. So, f of ui I should write in some terms of some summation of some numbers times vj, j equal to 1 to m. Right, that is true for each of these things. Say, so in general, f of uk can be written as a linear combination of basis vectors of v, right, that is v1 till vn, and let us say for each k I can write it something like this. If I just say f of u1 would be I equal to 1 till m c I 1 vi, and so on for everything, right. So, f of uk can be written, because f of ui is a vector in v, and therefore, it can be written as a linear combinations of basis vectors of v. Okay. And let us denote those coefficients as c, c I, k as set here. Okay. So, the coordinates of f of uk can be written in a vector form, and if I just generalize this to all n basis vectors u1 till un, then I can just write it as the map which transforms all these vectors u1 till un into v via the map f by just this matrix representation. Okay. So, every linear transformation f of an n dimensional subspace u into an n dimensional subspace v gives rise to an m cross n matrix A, whose columns consist of the coordinates of fu1 until fun, again with respect to the basis v1 till vm. Okay. So, so so I will have u1 till un. So, the f here is a matrix, should give me v1 till vm, and therefore, this is a m cross n matrix. So, m cross n multiplied with n cross 1 vector will give me a vector which is of dimension n m times 1, and if I just were to match the dimensions. Okay. So, therefore, this transformation is a m cross n matrix, and therefore, a linear map from f, so a linear map f from a vector space u to another vector space v can be represented as a matrix product. So, this f of x is simply a times x, right, where x belongs to u and a times x will be in v, right. A times x is this f of x. So, the conclusion here is that the linear map can be represented as a matrix or as elements of matrices. Okay. So, some real simple examples here. So, I have a linear map f x1 x2. So, this is like a map from R2 to R3, and I want to find out how the standard basis in R2 transform under this f here. Okay. So, what are the standard bases in R2? I have 1 0 and I have 0 1. Okay. Now, what is the matrix representation of this? The matrix representation of this is simply 1 and a 3, a 4, a -1, 2 and a 1 here. Okay. So, this is the transformation F or the corresponding matrix A, which takes elements in R2 and gives me a vector in R3. Okay. Now, how does F1 comma 0 translate in this side? So, I just look at this and just multiply this matrix A by the vector 1 0, and I will get the first column of this 1 4 2. Similarly, F0 1 will transform this way. I will just get the second column 3 -1 and 1. Okay. So, a little example of how the linear transformation essentially is related through elements of a certain matrix A. Similarly, you can do it for some other basis. So, here I just showed you illustration for the standard basis in R2, which is 1 0 and 0 1. You can similarly do it for other bases and check how these bases transform to under this map A. Okay. So, one more example. So, given a vector x in R2, find what is f of x in R3 via the linear map, which is again given by the same transformation as here. Right. So, that's again like a trivial stuff. You just substitute x1 equal to 1 and x2 equal to 2. So, this vector 1 2 will transform via this linear map, which has a matrix representation 1 3 4 -1 2 1 into, so this will be 1 and 6 is 7, 4 minus 2 is 2, this is 2 plus 2 is 4, right. So, this is how this vector 1 2 will look in R3 via this linear transformation. But and then you can still check some other some other properties also. Okay. So, what we just saw was about linear maps and how linear maps are essentially defined by elements of matrices, and we will do in the next lecture a little more on the properties of this subspaces. What are the more are some general results about rank and nullity, and then we conclude with the fundamental theorem of linear algebra. Thank you.